is Sonia DeBulio, and I'm the Director of Alumni Relations for the Faculty of Applied Science and Engineering. I want to thank each of you for being with us here today for our last Lunch and Learn presentation of 2021. I'm not sure where the year has gone, but there you have it. With alumni tuning in from all over the world, we have guests joining us from 9 different countries, including Canada, Hong Kong, Israel, Malaysia, Singapore, and the United States. Welcome, everyone. For those of you new to the Lunch and Learn, did you know that the Lunch and Learn was founded by the class of 1935? After they graduated, it was tough times for finding jobs. So the group used to meet monthly at Fran's restaurant on College Street, and the rest is history, as they say. Before starting today's presentation, I wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still home to the many Indigenous people from across Turtle Island, and we're grateful to have the opportunity to work on this land. Just a quick housekeeping item. At the end of today's presentation, we will have time for a formal Q&A. Should you have any questions for Professor Kortschot, please submit them using the Q&A button at the bottom of the Zoom screen. In addition, I would also like to thank everyone who submitted questions during the registration. We have shared your questions with Professor Kortschot and will continue to share any new questions asked during today's session at the end of the presentation. Now, without further ado, it gives me great pleasure to introduce our MC and chair of the Skule Lunch and Learn program, Laurie Hevola. Laurie is not only an Electrical 65 grad, but he is also one of our most dedicated and engaged members of our alumni community. Laurie has been chairing the Skule Lunch and Learn program for several years and continues to generously dedicate his time to maintaining the Lunch and Learn's long-standing established traditions. Just before I pass it over to Laurie, I do want to take a moment to wish all of those on the call today and to your families a wonderful and safe holiday season. Gosh, I think it's my first time publicly wishing people holiday wishes. And with that, I will pass it over to Laurie to welcome our speaker for today's event. Thank you.
Thank you, Sonia, for your very warm introduction. Again, it is my pleasure to welcome today's guest speaker, Professor Mark Kortschot, who will discuss the key principles of 3D printing and the possible benefits and limitations of this family of techniques. He is a professor in the Department of Chemical Engineering and Applied Chemistry here at the University of Toronto and is the former chair of the Division of Engineering Science. He obtained his Bachelor of Applied Science in 1984 and Master of Applied Science in 1985 in the Faculty of Applied Science and Engineering here at U of T, specializing in mechanics and materials science. He then went on to Cambridge University as a Commonwealth Scholar and obtained his PhD in 1989. He joined the faculty of the University of Toronto in 1988. Professor Kortschot is interested in both the design of materials and the design with materials. His academic research has centered on the relationship between microstructure and properties in fibrous materials, and most recently, he is focused on the mechanical properties of 3D printed composites. Professor Kortschot is also an active designer, inventor, and entrepreneur with expertise in materials selection, manufacturing, and intellectual property, and is a co-author of the textbook Designing Engineers, published by Wiley. He is a co-founder and president of Leger Reeds Limited, which makes premium synthetic saxophone and clarinet reeds that are used extensively on Broadway and in the world's leading orchestras. He is also the inventor of the Soul Skate, a compact skateboard licensed to Razor USA and chosen one of Time's top 10 toys of 2010. So obviously he does have some side hustles. In 2013, Professor Kortschot's commitment to education, research, and engineering design was recognized with a fellowship in the Canadian Academy of Engineering. And at this point, it's my pleasure to turn the presentation over to Professor Kortschot.
Laura, thank you very much for the introduction. I'll just carry on. Boy, that was a long introduction. Sorry about that, folks. Today, I want to talk to you about the practice and promise of 3D printing, as the title says. And I'm kind of going to break the talk into three parts, which align with my background and expertise. I'm going to share my slide with you. Let's go ahead and do that. And here we go. And so, yeah, so I'm going to break this talk into three basic parts. I know everybody's been reading about 3D printing, and many people know quite a bit about it already, as evidenced from the questions that we got before the seminar. And in truth, it's been around since the middle 1980s, basically. So I'll talk a little bit about that. But still, it's one thing to read about it, and it's another to kind of visualize exactly how it works. So I thought I would take the first part of the talk and show you the workflow from conceiving of a design all the way through the printer. And I promised a live demonstration, and sure enough, I have my 3D printer here. And we actually have time to sort of walk through those steps. Then the middle part of the talk, I wanted to talk a little bit about some of the other technologies that can be used for 3D printing, other than the one that I'll show you today. And in the end, at the last part of the talk, I will focus on the material science aspects, which relate to my research in the area. Unfortunately, I won't be talking about the field of bioprinting. It's not really something that I'm an expert in. And so, but I do hope to give you some general principles that would help you interpret articles on bioprinting. So without further ado, let's move on. So I'll start in a very basic way talking about the difference between conventional or subtractive manufacturing and additive manufacturing, which is the other word for 3D printing. And so I'm just going to flip back and forth to a couple of videos here. So bear with me for a moment. Here is a conventional subtractive manufacturing. We start with a big block of material and we cut away the bits that we don't want. It takes some time, of course, but that's how metals are typically produced still today on CNC milling machines, computer-controlled milling machines. So additive manufacturing is a little bit different than that. In this case, rather than taking away the material, we're going to put the material specifically where we want it. And so this is a slowed down video of the nozzle of a 3D printer. And effectively, it's like a glue gun with an XY stage. And so the stage is moving around underneath the nozzle, and the nozzle is spewing out a little plastic filament, a little bead. It's very thin. These layers might be 50 or 100 microns thick. And we're going to put it only where we need it. We put it down as a melt, and it solidifies in time. And we build the structure up layer by layer. So that's effectively how this works. So go back to my presentation. So let's focus in on fused filament fabrication, sometimes called fused deposition modeling, but that's a trademark term. So the generic term is fused filament fabrication. And this is a method of 3D printing that I've just shown you. It's a line by line, layer by layer deposition. And we're going to put the material through a nozzle only where we want it. So we have a thermoplastic, a meltable plastic that comes in a filament, in a spool. It gets fed through the nozzle of a miniature glue gun effectively. The stage moves around and we build up the part. And so, as I said, I wanted to take a moment and actually make that real for you and show you exactly how this works in practice. And I think we have time to build a small part. So we're going to walk through all of the parts of building this and actually get the printer beside me going. So the first thing we do is we design a part as a digital file. So I'm going to use a program called AutoCAD Fusion, which is it's actually freely available to hobbyists, and it's a very powerful program, actually, and not too hard to learn. Although it's not a few hours; it's a few days of learning to get going. And I'm by no means an expert. There are other simpler programs called like Tinkercad is a web program that is even easier to use. But ultimately, we're going to use a computer-aided design program to build a digital part, and one is pictured on the right here. We're going to take that and create an STL file. So the CAD program will spit out a file which basically describes the surface of the part, and that's called a stereolithography file or STL file. It's the standard way of transforming between a CAD program and a 3D printer. The next step is to slice that file to send it to another program, which also is something that is freely available. And what that program does is it takes the physical part that is described by the STL file, and it converts it into a set of instructions. Exactly where is the filament going to be laid down in what sequence and so on. And it creates something called G-code, which is what all 3D printers and CNC machines run on it. The code is called G-code, just basically saying, go there, do this, go there, do that. That's the set of instructions the 3D printer actually gets. We send it to the printer, press go, and we come back in a few hours to inspect the solid part. So I think we should do a demo, as I said, and I'm going to just share a different screen now. So let's start with Autodesk Fusion. As I said, that's the program that I'm going to use to build a part. And here's the part that this is pre-built. So this is, and it's a three-dimensional part, and I will show you that this is the part that has been printed on my printer, my home printer, that to correspond, and it corresponds effectively exactly to the digital file that we created. But I promised we would start from scratch, so let's do that. So here's a blank canvas, and what I'm going to do is just create a very simple part. So you don't need to follow all the steps, but hopefully you can see how this works. I'm going to create something. I'm going to make it very simple. It's a box. I'll put it on this plane, place the first corner, maybe place the second corner. So I'll make it, well, let's make it 40 by 30, something like that. And it's 1 millimeter high. I'd like it a bit thicker than that. I'll make it, well, let's say 10 millimeters high. And okay, so now I have a solid part that's been created. I could send this to the printer. Let's make it a little bit more interesting. I'll put a hole in it. And I want to make the hole here, for example. I'm going to create a custom threaded fastener. And here's some details on the right-hand side that you can see. It's a simple hole. It's a tapped hole. And we could countersink it. We could do a number of things. Yeah, okay, I'm happy with this. Now I have a 3D part. Can rotate it. It's ready to go. It didn't take me too long. It's a simple part, but obviously the more complicated it is, the longer it will take. And so what I'm going to do, I'm ready to print. I'm going to send this to the 3D printer by choosing 3D print from the drop-down menu. And I need to select which part is it that I'm going to print. So this is the one I want to print. And what happens is that the part is now, the surface of the part has been represented as a series of connected triangles. So the STL file is actually a description not of the solid, but of the surface. But the surface is closed, so it incorporates the solid part. And so, again, this is the part I'm interested in. I'm going to accept this part, and yeah. So now an STL file will be created. And the next part of this process, I need to share a different screen because it's been sent over to the slicing program. And so hopefully I'm not going too fast. This would be much better as an in-person presentation. So I'm just trying to give you the sense of basically how straightforward this can be. Now I'm sharing what's called the slicing program. This is like a physical picture of the bed of my 3D printer. And here's the part on it. And we can choose how we want to print it. There's lots of settings, but the default settings are fine. So I'm going to choose 200 micron thick layers. That's up in the top here. I'm going to choose a 15% infill. So I don't want to waste too much filament. I'm not going to print it as a solid block of polymer. I'm going to let the center be hollow. I'm happy with all of this. I'm going to slice this, so convert this into instructions. And now what we can see is we see the part, and actually these little beads that you can see represent filaments. Let me cut down through the part digitally so that we can see exactly how this is going to be built. So I'll start at the bottom. And here's the first layer, first couple of layers that are going to be put down. And if we zoom in, that is actually, these filaments are the filaments that are going to be laid down by the nozzle in a zigzag 45-degree pattern. If I step up one notch, that's the next layer. So the printer head will move up one notch, and now it'll lay down the second layer. Again, it's like a glue gun, it's just miniaturized, basically. And now we're into the area where I'm going to have the infill. I said I didn't want to waste filaments, so I'm going to make this a sparsely filled solid. And the fill pattern I can choose, but this is the one that's fast and was decided by default. And it builds up. I'm walking up through this part. This part is only 10 millimeters high, by the way, for scale. The threads are being printed. Everything is being printed. I'm happy with this part, okay? So I'm happy. I can change settings. I can make it coarser. Oh, sorry for the motion sickness here. I can make it coarser. I can, there's a whole variety of settings that can be changed, but I know that by default, this part is going to print okay. So the next step is to print the G code, and I'm going to actually stop the share there and share camera so that and I'm going to choose a different camera here. Hopefully you're looking through at my printer at this point in time. And so here's the printer sitting on the side of my desk, and it's a Prusa Mark III. It's made in the Czech Republic. I've already preheated it. It's ready to go. And I'm going to print from the SD card. This is a part that I just designed. Actually, I cheated a little. I preloaded a part that's identical that I designed yesterday, but it's as fast as this to send it across. I'm going to print that part. And the bed is already hot. So let's just take a moment and watch what happens to the printer. It's all ready to go. The first thing that happens is that the printer is going to level the bed. So the printer, the layers are very thin. They're only maybe as low as 50 microns thick. In this case, I've chosen 200 micron thick layers, 4 times the diameter of human hair. And so we want to make sure we know exactly where the base plane is. And now this is the filament is here, of course. It's being fed down into the nozzle. We're just throwing some filament down to clear the nozzle at this point, and we're printing. So already this is printing. And I know from the screen that this is going to take 32 minutes. I know from the software that it'll consume about 2 meters of filament, and it's already printing. I don't really want to have this running while we are, because of the noise while we're doing. So I'm going to cheat a little bit and do like the cooking shows. But there's the first little bit of filament that's been laid down. And I basically designed the same part earlier. So if we came back 32 minutes from now, that's the part we'd be looking at. We'd snap it off, and yeah, ready to go. It's light because it's hollow, but it has the threads, everything. It would be a perfectly dimensioned part, very comparable to what I've designed in 3D. Right. Oh. Let's flip back to the other camera here. So that's it. That's the entire workflow for 3D printing. Basically, I went all the way in some period of 10 minutes or something like that, from the desire to have a part, especially threaded nut, designed it in CAD, sent it to the printer. I skipped the 30 minutes of printing in between just to avoid the noise on the printer. It's a little bit noisy, but it's pretty quiet, and we end up with a physical part in our hands. So something a little bit more complicated like this part is, this would take something on the order of hours, maybe 10 hours, 20 hours. So I've had parts that print for over a day. But ultimately, you print, you come back, and you have the physical part in your hand. Let me go back to sharing my presentation then. All right. All right, so there are some alternatives to this that I just thought I'd discuss, just as we're still talking about the workflow and what it takes to actually get printing. So we'll spend another 5 minutes on that, and then we'll move into some of the printing technologies. So there's some alternative workflows. Instead of designing the part yourself, you could just pull a CAD design from the web. And so for those of you that have done any machine design, you'll be familiar with the company McMaster Carr. McMaster Carr is a company that used to have a 6,000 page paper catalog, but now it's all online, of course. But it's a place where you can order mechanical components, gears and sprockets and whatever, all hydraulics, all kinds of components. And they upload the CAD for all of those components, the computer-aided design files, so that you could build a machine with those and incorporate those gears. But there's nothing to stop you from just taking that CAD, bringing it into Fusion, and printing that gear if you wanted to make a prototype of your machine. So that's one thing you can do. A second thing you can do, there are lots of hobbyists on the web, and they're repositories of designs that people post for fun because, so if you wanted to print a chessboard, no problem. You can go and download thousands of different designs for chess pieces and just download them to the printer and print very easily. This part I'm showing you, I actually printed. I had a set of Oakley sunglasses, Oakley jury sunglasses. There's a plastic part in the arm that broke. And I went just on spec to see, has anyone designed this? Somebody had already CAD'd and designed that part, and I was able to download that file and print it. So there's a big repository of pre-existing prints. There's also another thing, which is that you can scan objects and create that STL file. So I went back to the Thingiverse, which is this repository of designs, and this person has designed a mount for your phone and a crank, a turn wheel to sort of basically a little turntable. And this is to use the scanning features of an iPhone to actually do a 3D scan of an object. And so from that, so you put an object on the turntable, you turn it. I haven't actually done this myself, I confess. And the output of that scanning process is an actual surface, a 3D model, which you could then send and print and sort of physically replicate in plastic, this thing that you've scanned. So you can design or you can find files and print them. Those are the kind of main things. Cindy asked for some recommendations about low-end printers. I'm not going to make any specific recommendations, of course. I use it. This is from the Czech Republic. The machine I use, it's a Prusa Mark III. It's a fantastic machine. Frankly, it's never let me down. But here's just one I pulled up from Amazon. They can be very cheap. I do recommend spending a little bit of money because, the thing like bed leveling, knowing exactly where the bed is and so on, it could be less hassle to spend a little bit more money, but I have no comment on this particular printer. It has good ratings on Amazon. It's obviously very inexpensive. So these are all fused filament printers. So this very simple print technology we're talking about, it's the most common kind of home printing technology. If you don't have a printer and don't want to buy one, in Toronto at least, the libraries have them. All of our undergraduate students have can print in our brand new My Hall fabrication lab, our light fabrication facility. So they're in very good shape, undergrads and grads within the university. John asked for reasonable cost places to print. I don't know what the costs are. You probably pay per meter of filament, and you can do it in libraries. There's lots of little clubs and so on as well. It's not too hard to find. They're called maker spaces. So if you're looking for the code word to find this community, they're called makers, and places are often called maker spaces. And if you have a more demanding application, maybe you want to print in metal or print production parts or some other technology. Of course, there are professional service bureaus that just have printers and run them all day long, and that's their business model. I have used this one in Vaughan, Ontario before. It's Proto 3000. It's just one of many professional service bureaus. So that's a first part of the talk, just a description of how to move from a CAD, an idea, to CAD through to a printed part. And I want to move on now and just talk a little bit about printing technologies and give you some fundamentals of printing technologies that you can invent your own printer then if you know the basics. And so essentially, I mean, there have been printers designed around all of these fundamentals, and there's probably not a lot of space left for brand new printers, but I'm sure there are things that you could do to generate a new technology. So let me talk about a few of them. The first one that we talked about in the upper left here is we can deposit a liquid. So all of these involve creating a solid only where we want it. So here are some techniques we can use. We can deposit a liquid and then solidify. So in the case of the fused filament, we melted a bit of thermoplastic polymer. We put a line of it where we wanted it, and we let it freeze in place before we put any more down. But there are other techniques that you could use. So you could deposit a liquid and then chemically cure it. So two-part epoxy is not melting and freezing, it's liquid and then it chemically cures. So I could, in principle, create a 3D printer with rapid setting two-part epoxy just by squeezing it and mixing it and dropping it where I want. But also UV can be used to cure some thermosetting materials, thermosetting polymers very quickly. And even drying works. So you can deposit a liquid and then just let it dry. So if you've decorated a cake, you've participated in additive manufacturing already. You've squeezed some icing out where you want it and you let it dry. There are some other techniques though. One is to selectively solidify parts of powder. So if you imagine a box of powder and you can hit it with a laser beam and just let it solidify where you want the solid to be. Or maybe you put in some glue where you want the solid to be. So you'll bind the powder with a polymer binder. We'll come into some specific examples of all of this. And the second, so fused filament is the main kind of 3D printing technology that you read about all the time. The other one is called stereolithography. And this is where we have a liquid vat in the original configuration. There's a liquid vat and we hit it with a laser beam where we want the solid to be. And then maybe we drop that part one unit and put a new film of liquid across the top, hit it with a laser beam again. So those are some of the technologies. One ancillary thing we need to think about is the idea of support. And so this is, I'm looking at printing a bed here, and for some reason I'm printing these boxes beside it. And now the reason becomes obvious at the end, because I want to print something that's overhanging. And if I let the filament squeeze out of the nozzle and just print it into free space, it's not going to stay there, of course. I can print at an angle, maybe 45 degrees, perhaps even more. So I can print an overhang that's 45 degrees, but if I have a 90-degree overhang, that's not going to work in my printer. So what we do is we print a series of supports, and then we have to remove those supports after the fact. So we either take them out with a pair of pliers, or we dissolve them, or some other technique, and we're left with the solid part at that point. Let me share an interesting mega application of this deposition, this filament deposition process. So I'm going to go back to Chrome and share this with you. We'll go to the next one. So this is a 3D printing of houses. So this is concrete cures with time, and it's fairly viscous, fairly solid. So this is a giant version of my 3D printer laying down a bead of concrete. This is like a truss system, and the concrete is thick enough to sit there until it chemically cures. Concrete cures over time, as opposed to drying. Just, excuse me, I just have to bounce back and forth here in order to make these videos work at a reasonable speed. So let's talk about some other technologies. We could have a jetted UV, so we could put polymer down and then hit it with a UV light immediately, either through multiple nozzles or a single nozzle. This is called a polyjet, so multiple nozzles lay down a sort of a thick resin, which is UV curable, and right away I hit it with a UV light to solidify it in place. But then other than that, it's similar to the printing that I've already shown you. The next one is a little bit different. So this is selective laser sintering. The workflow starts the same, CAD, CAM, and so on. But then instead of putting a solid down through a nozzle, in this case, if we look at the right-hand side here, we're building the solid part on the right. We have a bed of powder, and we hit it with a laser beam to solidify it where we want. Then I drop the bed one unit, push another powder film over top, sprinkle a little powder on top, hit that with a laser beam, and so on. this is called selective laser sintering. It's another major class of 3D printing. And the advantage of it is that we don't need support because the solid is sitting in a bed of loose powder. At the very end, I reach in, pull the piece out and shake the loose powder from it. And that powder could be polymer, but it could also be metal if the laser is sufficiently high powered. So we could create a laser fused metal part in this way. And that would be a much stronger part. A number of you asked about part strength, and I'm going to talk about that in the last part of the talk. One of the other original, this is analogous, but this is one of the other original 3D printing technologies from 1984, I think, the original patent. So this is called stereolithography. That's where the STL file gets its name. In this case, I have a vat of liquid resin and a support platform that's descending into that vat. I put a layer of liquid resin over top of the part, and I hit it with a laser beam or UV beam to cure it where I want it. Can be a projector as well. And I make the solid only where I want it by curing the liquid polymer as the part. And then each time I create a layer, it's always layered. So it's very similar to before. And then the liquid resin drops away and I'm left only with the solid part. So that is called stereolithography. And the other sort of main kind of printer you might see at home is something which I would call inverted stereolithography. So the problem with stereolithography, or one of the problems, might be that if you hit it with a laser beam, you can have some partly cured molecules left in the bath. And so you might not be able to reuse the polymer bath again. So what's happened is that it's been flipped upside down. And so now we have a platform that descends into the bath. So if you look at the right-hand side here, here's a platform. And this is the first layer that was printed, the layer right next to the platform. It's up in the top right. The platform descends into the bath to within 50 microns or 100 microns of the bottom of the bath. The tray is transparent. The laser beam comes up from underneath to cure it and stick it to the platform. And then the platform lifts, and then I cure the next layer. And so I can get away with much less resin in the bath. And I'm just going to flip back to the videos that I've got here. So to show you kind of a schematic of how this works. This is a Form 2. This is quite a good quasi-consumer, almost a prosumer level printer, I would say, personally. And there's the platform descending into the bath. And here's some of the mechanics. They use a laser beam, which they bounce around through the tray from underneath, boom. And they cure the part layer by layer and pull it up out of the bath and then the part goes. Now they use this sideways swiping motion to dislodge the part from the bath. Then they drop it down to within 100 microns or whatever the distance is, 50 microns, cure the next layer, lift again. And again, you're building layer by layer. And this is a relatively slow process. A very clever modification of this process has happened in the last, I think, 5 years, and that's by a company called Carbon 3D. And let me explain how this works. This is the same inverted stereolithography. That platform is going to descend into the bath of resin, and in this case, I think it's a digital light projector, so they print the whole image as opposed to a single laser beam at once. But they've done something incredibly clever, which is that the bottom of this tray is porous to oxygen. So they're curing the layer that's right next to the tray. I'm going to run the video here. This is run at 14 times the speed. I actually doubled this up. They're curing the layer that's right next to the tray, but they're also feeding oxygen through the tray. And what that does is it prevents the material, it inhibits the cure and prevents it from curing right at the tray surface. So the solid is never actually connected to the tray, never sticks to the tray. And they can essentially pull this part continuously. That was 14 times the speed. They can pull that part continuously out of the bath because it's never stuck to the surface. It's really a fascinating technology. Share that instead of this random video. Did want to say a little bit about the history now, and I'm going to talk about material science next, but let me say a few words about the history. The main technology is the stereolithography and the fused filament fabrication were invented in the 80s, and patents last for 20 years. So 90s, the aughts, that those patents expired. And that is when those original foundational patents expired, that is when we saw an explosion of 3D printing. It was pretty much used by industrial designers in the interim, but then suddenly that's when all of these 3D printing technologies became home use. So all of these 3D printers, Kickstarter is a place where inventions go to get their start. And I can tell you that hundreds and hundreds of 3D printers began around 2010. It was a real explosion of interest as the original foundational patents were expired. Maybe I should go back now and talk about a little bit about the motivation for additive manufacturing. And there's a few motivations. Firstly, of course, it's quick. So we can go directly from a digital file. We don't have to make a mold. We don't have to do any slow and expensive CNC machining. We go right from a digital file to a prototype. So I showed you earlier, a prototype of a design, but that design went through several evolutions. So it got a little better, and then it got a little better. And each time those parts could be printed and tested and to see if they were good for fit for purpose, just as not as production parts, but just as parts for inspecting the design. So we do this rapid prototyping. It can be functional. You can print gears and so on. Another thing you can do is you can print parts that actually can't be made by conventional means. So here's a part that's got internal channels that would be impossible to injection mold or machine, but we can build it by any one of a number of 3D printing technologies. Another use case is to have short run parts. So like for medical equipment, where we're only going to make maybe hundreds of components, or aerospace, we're only going to make 500 of this kind of plane and it needs a particular part. This is a patent application for a digital parts library. So now instead of keeping a warehouse full of spare parts, we keep a digital warehouse full of spare parts and print them on demand. So if the performance of those parts is adequate, then you could just have a digital warehouse. But this is only for, so far anyway, it's only for short run parts, not for parts where we want hundreds of thousands of parts. So my printer is still relatively slow compared to the process of injection molding. And I'll touch on that in a moment. And the last use case is custom parts. So this company, Unlimited Tomorrow, is now sending you a scanner. You scan your limbs at home, you send them the digital files, and within a reasonable period of time, and for a very modest cost, you get in the world of prosthetics, certainly, you get a kind of bionic arm that matches your opposing arm perfectly because you've scanned your opposing arm, all done remotely, all done by 3D printing. Fascinating. Okay, last part of my talk now, I want to talk a little bit about the material science. And about the strength of these parts and why there's, some of the limitations. So when we're building a non-functional prototype, so here's a prototype I'm holding up. Again, it's this little part rack, and I built multiple types. I don't really worry about the mechanical properties, but if I want this to carry load, I am a little concerned. And this part, it's been printed in 2 different filaments. I just changed the filament color from gold to black, not just stop the print and change. So that's nothing special about that. But one thing is this part is printed in layers, and it's actually quite, I'm going to destroy it on camera here. It's quite brittle. It's not too bad in this direction, but in between the layers, they're not bonded as well as they are in the plane. And the reason for that is that we're relying on polymer diffusion. We're putting a molten bead of polymer onto polymer that's already solidified. These polymers are made up of very long chains. That's why they're so viscous. Those chains do not like to diffuse into one another readily. So some polymers work much better than others for 3D printing. But there's always going to be this issue where the strength between layers is, I won't say there'll always be this issue, but typically in a typical fused filament fabrication, the strength between layers will be a little lower. We might leave a little bit of porosity in the part. So there are some kind of limitations. Now let's contrast that to injection molding. So I'm going to quickly share an injection molding video. So let's have a look at this. So this is a typical injection molding. If you're not familiar, solid polymer granules are fed into a barrel. They're heated up and melted. They are then squeezed into a mold. So here's a closed steel mold. Here's the interior of it, shown in cross section. I'm going to squeeze the polymer in, and there we go. And then we let the mold cool, and finally the part drops out. So that's a solid part, and there isn't this interdiffusion problem because it was all molten, all solidified at the same time. So sharing again, holding up, I'll just hold up the finished part now. This is a part which has been injection molded after all that work. The CAD was 3D printed, we checked it, but ultimately we used the CAD to make a steel mold like the one I just showed you and squeeze an injection part, an injection molded part. And this part is made in, I don't know what the length, the cycle time is, but it's maybe 30 seconds or a minute at the most. And it costs very little money, and it can be made in large numbers, and it's relatively strong because of the way that it's been manufactured in injection molding. So to answer one question about the mass distribution of, are we going to switch all to digital 3D printing as we've switched to largely to digital paper printing? My answer to that is maybe for some, maybe for metals, as we'll see, but for polymers, and large runs of parts, injection molding is still a much less expensive and much quicker way to make good parts. So can we do better with our 3D parts? And I've got about 5 minutes left, so I just want to touch on some higher performance 3D parts. Gary asked about anisotropy and high strength filaments in the questions before we started. And so yeah, it is possible to print fiber reinforced plastics. So in my printer, I can use a fiber, like a glass or a carbon fiber reinforced filament, and just print it as normal. And when I do that, what happens is the fibers tend to line up. There's extensional flow in the nozzle of this printer. You can see them on the surface on the left-hand side. You can see a cross section, a tomography cross section. The fibers are nicely lined up. And and so this filament now is quite anisotropic. It's stronger in the filament direction than it is in the cross direction. And at the very beginning, when we saw the filament laying down, even unreinforced filaments are, because of the filament direction, they're a little stronger in the filament direction, and the printer naturally laid down subsequent layers at right angles to each other. But it's especially important if we were to use fiber reinforced filaments. We make thin layers, and we would lay one layer down at 0 and the next one at 45 and minus 45 and 90. And that's how we would get a material, a sheet, which was strong in all directions. And this is normal for composite manufacturing, even conventional manufacturing. And we've done, this is some of my material science research, so we've investigated the effect of how you lay these, how you build this layered structure up on the strength, and particularly the modulus. And when all the fibers are pointing in one direction, it's stiffer in that direction, but it tends to be brittle and can snap in the transverse direction. So for sure, in a sheet, you may want to lay down some layers at angles. And we actually, in composite mechanics, we have very good theory to predict exactly how these things are going to behave. But interestingly, right now, I'm not aware of any commercial software that will allow you to control the build based on the need for mechanical properties. Even stronger, I'm not going to show this video, but even stronger, Mark Kortschot is a company that is actually reinforcing polymers with continuous fibers. So they're taking continuous fiber, carbon fiber off a spool, mixing it through the nozzle with a polymer, and that's making actually an extremely strong material. It's sort of comparable to aluminum. So there were some questions about very high strength parts. Yes, I can build tensile parts. I can build very high strength composite parts using a technology like that. And the printer is very similar, but more sophisticated than the home printer I have here in the office. And just another little bit of research that I've done. I was interested in seeing whether in the inverted stereolithography we could add fibers to that. So I had a master's student work on this, and we'll see. But what we found, we were trying to print a long specimen. We want the fibers lined up in the vertical direction, in the long direction. So we bring the build plate down when the specimen is partly built. And what do we see? The material gets squeezed out sideways, and actually the fibers line up in the wrong direction. So it's the opposite of what we wanted. And so that was one of the findings in this little bit of work we did on inverted stereolithography reinforced with fibers. Here's some nylon bristles in a bath of soap, and I'm looking down from the top. I'm squeezing the build platform down, and you can see those fibers getting pushed in the transverse direction, which frankly is not what we want for high strength materials. I've only got, I think, a couple minutes left. I'm almost done. So I did want to say something about printing with metals. So we've talked mostly about printing with polymers. I have a polymer and composites background. Printing with metals is also possible. I already talked about selective laser sintering in a metal powder bed. So you can just hit a powder bed with a laser and create a solid part layer by layer. But there are some less expensive and new technologies more recently. So there's a couple of ways of printing that powder and just binding it. So we could have a powder bed with some polymer coating on the metal particles, and we could hit those with a laser beam, a lower power laser beam, low temperature, glue that all together, the metal together. Or we could filament print with a metal powder filled filament. And in that way, we could make a part that is metal particles bound together with polymer. And then what we do is we remove the binder and sinter the part into a solid metal part. And sintering is just like heating it up, but not melting it. So it keeps its shape, it shrinks, and we have to account for that sintering shrinkage. But of course, that's all done automatically in software. And it is possible then to pretty rapidly build a metal part this way. And it takes a little while to sinter it, but at the end you have a metal part, which, because the metal doesn't have this problem with diffusion, it's a pretty strong, highly dense metal part at the end. So I'm just going to flip to the conclusions and say thank you very much for your attention. I think summing up, there's a very low barrier to entry for sort of simple industrial design type applications, trying out new designs, seeing what they look like in real life. You can build, there can be some strengths. So certainly you can build functional parts that do a job, wide range of materials. There are new applications coming all the time. And we're not going to replace all conventional manufacturing. Injection molding is an example. But certainly, I think increasingly 3D manufacturing will supplement conventional manufacturing. And finally, I haven't discussed bioprinting. It's a very rapidly expanding area, but all the same basic principles apply. If we can deposit a solid selectively and then and it's a biomaterial, fine. We can create tuned bioscaffolds that will be functional parts, and the material, the compatibility and so on will just depend on which materials we're printing from. So with that, I'm going to thank you very much for your attention. I'm going to stop sharing. And I'm going to go back to the camera and answer any additional questions we have. Lori, thank you.
First of all, thank you, Mark. You really prompted a lot of questions. We've got 11 questions online, so I don't need to revert to the questions that were sent in before the meeting. I'm going to go through some of them fairly quickly. First, Greg Dow is asking, are 3D printed parts recyclable?
Sure. So this 3D printed part is made out of pure polymer. So if the polymer is recyclable, if it's polypropylene or PLA is the common 3D printing material that we use at home. But if it was a polypropylene part or a nylon part, it would be recyclable in the same way as a regular part. Composites are harder to recycle, actually, to be quite honest. So when we put fibers in, that does present a challenge.
Next question is for Doug Carson. With the part you printed that we saw, how did you keep the top surface from collapsing into the hollow space below? Oh,
great question. So yeah, we didn't print any supports in that, but so you need a support if you have a large overhang. But actually, there's a little bit of tensile strength in the filament. The filament has some tenacity, I guess, or tensile strength, so it can bridge small gaps. So if we looked at the first layer that was printed on top of that hollow scaffolding, we'd probably see a little bit of sagging. But then by the time we print the second layer, and the top surface was like 3 or 4 layers, the top surface is absolutely fine. But definitely, you can do some bridging. Actually, you can do some pretty extensive bridging without the supports.
2 questions. One, Olivia Passaran, and the other one, Vlad Passaran. What mobile app can you use to do the scanning? And the other question, what was the software that is used for scanning with an iPhone?
Yeah, I have not done this. I have to confess, so I don't know. I know my iPhone is capable of scanning rooms. I have one of the newer iPhones. It's capable of scanning rooms, and I'm assuming that based on, I believe that it can scan physical objects of kind of, not microscopic, but like chess pieces or something like that. I can't comment on the resolution or exactly what software to use, but I'm sure there's tons of information available online. I just stumbled on that little stage that was 3D printed. You 3D print that stage, and then it gives you a beautiful rotation and allows you to scan the whole surface. I can tell you that another application, I didn't want to show it, but I recently went to have a dental bite plate, bite guard created, and they digitally scanned the inside of my mouth, all my teeth. So I didn't have a mold made of my teeth as I would have in the old days. They digitally scanned my entire mouth. They 3D printed my mouth, and then they built the bite guard on that, and it fit perfectly. So I didn't want to show you that, but yeah, that's another application with a specialized medical scanner.
Thank you. And next question from Amaya Papali. What are the typical glitches normally encountered with 3D printers?
There can be problems. So if a layer is missed, or something doesn't bind and it gets stuck on the head, it's possible to come back the next day and find a big plate of spaghetti, basically, because the printer's been running all night laying down filament, but there's been some kind of collapse or mistake. A good print, so the cheaper printers don't have any way of avoiding that. The very cheapest printers, I guess. Even my Prusa, though, it has like a filament. It will detect if the filament's not feeding properly or if there's a jam. Modern printers, so it will detect some of the things that could cause problems in a 3D print. And I have to say, mine costs about $1,000, by the way. I don't own any shares in this company. I just like the printer, and it's been pretty robust. A few times the prints have failed, but it's pretty uncommon, actually.
We're going to try with a couple of more questions to end. From David, who asks the question, I understand that UL and CSA do not accept 3D printed parts for product certifications. Is this still the case and or likely to change in future?
I don't have any expertise. I'm sorry, I don't know. So 3D printed parts, everyone in print, so when we injection mold parts, they're very consistent. When we 3D print parts nowadays, they're also extremely consistent, but you could change the temperature of the nozzle and print something that looks the same and yet had a different strength. So I presume that's where the reticence is on part of the approval authorities. But I must say that, increasingly there are big companies that are using banks of printers to sort of, print short runs of material. And I can't comment on the legal framework, I must say, but I'd have to believe that we're moving in a direction where we'll be using it more and more. So take that for what it's worth.
Thank you. Question from Leon. Unless I am mistaken, I think you mentioned that an injection mold can be 3D printed in metal. How does that compare in price to the conventional method of making a mold? And are there any limitations doing it in 3D printing?
Wow, sure, great question. So I don't think I quite said that, but let me comment on it. Certainly, you can print metal, so the intuition is absolutely right. There's no reason that you couldn't print a metal mold. Actually, I've got a little part here. This is a 3D print. It's an injection mold, so it's a matched mold. I can't squeeze plastic into there because the mold will melt. If this was metal, obviously I would be able to use it. I use this to mold some casting, some silicone. I could put 2-part epoxy in here and close it up, come back later, pop the part out. I used it for some silicon molding compound. But if we make this out of a thermosetting material, like we use the inverted stereolithography and maybe with a bit of filler, that material doesn't melt anymore. It's chemically cured. So you can make a mold out of a polymer actually that's capable of, molding some low melting temperature polymers for short runs before the mold sort of, erodes a little bit. I don't know much about making molds by injection molding. By 3D printing the mold itself, but it's a perfectly reasonable suggestion that we could make for a short run. The problem would be resolution. So, I mean, the difference in resolution between a 3D printed part and the final part is, pretty profound. So this has a texture on it. It's got even like a little texture, some gloss and texture. So that kind of detail is at a level that a 3D printer can't, because it's a digital process, is not replicating. But of course, they get better and better all the time.
Thank you, Mark. I think at this point, we'll begin to wrap up. Thank you to the audience for all of the questions today. I didn't have to revert to these questions submitted in advance. Before we close, obviously, I would like to thank Professor Mark Kortschot for being with us today. Thank you for such an informative and entertaining presentation on 3D printing. Thank you also for campus events for providing the technical support that made this online virtual lunch and learn so successful today. To everyone who joined us here today, we invite you to share your feedback on the Skule Lunch and Learn series. Shortly, a link to our online survey is going to be made in the chat and will be shared with all of you after this event by email. We would ask that you please take a moment to fill out the survey, as we have included a new question asking you specifically about your current level of interest in attending in person at a small cost if this option were made available to you in the future. We were hoping to resume in-person lunch and learn events at the faculty club in the new year. However, we are not quite ready to do so, so it's important that you provide your input to this question. In addition, a link to today's presentation will also be shared with all registered guests early next week. The Skule Lunch and Learn events are traditionally hosted on the second Wednesday of each month. Our next Lunch and Learn event will be online on Wednesday, January 12th, featuring Professor Erwin Sedgwick from Electrical and Computer Engineering. For more information about this Lunch and Learn presentation, please visit the Skule Lunch and Learn website. I would also like to acknowledge and thank MBNA, the sponsor of Skule Lunch and Learn, through U of T's Pillar Sponsorship Program. If you're interested in learning more about Skule Lunch and Learn series, please contact the alumni office at events@engineering.utoronto.ca. In closing, we would like to thank all of you for joining us today for today's presentation. Hereby adjourn today's session of Skule Lunch and Learn. May all of you have a wonderful holiday season, and we hope to see you in the new year. Thank you and have a good day.